Alright, gang, here we go. This is for Physics, Unit 6, Part 2. We're talking about fluid mechanics. So here we're going to talk about pressure. We're going to talk about Pascal's principle. Talk about a couple other things. Should be fun. Alright, so first of all, pressure, just a brief recap. This should be something that you're already familiar with. Pressure is defined as a force applied over an area, force over area. Okay, and so this is, when we were in physics, we talked about kinetic molecular theory, right? Or chemistry, excuse me. We talked about kinetic molecular theory. We talked about how if you had a balloon, right, and it was filled with all these gas molecules, and these gas molecules were bouncing all over the place, and they were hitting these parts of the balloon, kind of going each way, whatever. Okay, and they'd go and they'd hit the walls of the balloon, right? And so if we blew up on the balloon, we'd have all these molecules that were running into our balloon, and this force that they're applying on the balloon is being equally applied to the force of the atmosphere pushing down on it, and that's why it has the shape that it has, right? And so it's this force, and force is mass times acceleration. So these particles have mass, and they're moving at a speed, and that so they have an acceleration. Okay, and so they're running into the walls of the balloon, and then that's creating this force. So it's a force over an area. Okay, so force, the units for force is in newtons. Okay, our SI unit for area is in meters squared. Okay, so we have newtons per meter squared. All right, so that's our SI units, and they're also referred to as the Pascal, PA. Okay, and Pascals are actually pretty tiny. Okay, 1 Newton is not very much, right? You've already experienced that. It's just 1 kilogram. Okay, moving at one acceleration, and so that's not very much. Okay, and so 1 Pascal is actually a really small amount. So atmospheric pressure, okay, is something around 10,100, okay, pascals, or 1.01 times 10 to the fifth. So really, in a lot of ways, like, we don't use pascals. We'll use pascals quite a bit, but in the real world, okay, atmospheric pressure, is a lot of times you'll see you'll see pressures in Pascal and kilopascals, which would be 101 kilopascals. So on and so forth. Okay, but anyway, so essentially, okay, atmospheric pressure is quite a lot. It's 100,000 newtons of force on each square meter. That's a lot, right? Okay. Another way to kind of think about it a little bit different is that we is a 14.7 psi is about what atmospheric pressure is, and psi is pounds per square inch, and those are garbage unit pounds, that we use in the grade US, right? Pounds per square inch. Okay, so really what you're saying is that for each square inch of surface that you have, so that's about the size about that and that or so, there's 14.7 pounds of air pressure pushing down on it. So like on your hand, holding your hand up is actually a pretty impressive feat. You're actually quite strong. Congratulations, because there's 14.7 pounds pushing down on your hand for each square inch. It's not an unreasonable amount of force. So congratulations, you are stronger than you thought. Okay, so anyway, so fluid pressure. Okay, now pressure inside fluid gets kind of interesting. All right, now this now, based on what you already know, this should already make sense. Okay, so Blaise Pascal discovered that fluid pressure depends only on the depth. Okay, it doesn't matter how big of a fluid that you're in. Okay, if you're at 2 meters below the surface of a kiddie pool, okay, or a backyard pool, okay, the pressure experienced at that depth will be equal to the pressure experienced if you were in an Olympic-sized swimming pool. Okay, so it doesn't really matter, or the ocean, right? If you're 2 meters below, the pressure experienced at that depth should be equal, and that should make sense to you. Like if you're in a closed-off room, okay, that's at at sea level. Say you're visiting the beach in Florida or California or something like that. You're in a closed-off room there. Everything's completely sealed. Versus if you're in a closed-off room out in Colorado, you're out skiing. Okay, the pressure you experience in that closed-off room, okay, in the mountains, will be far less than the pressure experienced in that closed-off room. At the surface of the ocean, or at the surface of the ocean. Okay, so essentially fluid pressure only depends on the depth. Okay, the other trick to think about in fluid pressure is that if your fluid pressure increases at one point in a fluid, it is increased equally at all points. Okay, and this makes sense. Like if you take like a balloon, okay, and then you walk with it. You blow up that balloon at the top of a mountain, and then you walk it down to the base of the mountain where the pressure is increased. The volume of the balloon doesn't just increase in one spot, right? It's not like all of a sudden your balloon got dented in one place. The whole volume of the balloon decreases continuously, like or equally across the whole thing, and that's because the fluid pressure it's increasing in one spot, but it's also increasing everywhere. Everywhere around that balloon, the air pressure is pushing down equally hard. So as you go down in fluid pressure, okay, if you're like submerging an object like a submarine or something like that, your fluid isn't going to be just pushing on one part of your submarine. It's going to be pushing on equally across the whole part of the submarine, and that's part of the trick as to why submarines can function at such low pressures, is because they're specifically built that as you go down to certain pressures, the pressure pushing it on all sides will actually help reinforce the hull integrity. Okay, so it's kind of a neat engineering trick. Okay, and so this idea here is known as Pascal's principle. Okay, pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and to the walls of the container. All right. Okay, and so we can use Pascal's principle to come up with one practical application of these is hydraulic lifts. Okay, and we use these all the time, and they're super helpful. They allow us to lift things more easily than what we should. So if you've ever changed the oil on your car or something like that, you've got your own jack, and using hydraulic lifts, that's the whole idea. You're using a fluid that's in the jack, okay, in order to apply a force that you shouldn't necessarily be able to without it. Okay, so it's kind of like using a simple machine, but it's really more complex than the simple machines we've talked about in the past. Okay, so what's going on is that we know that based on Pascal's principle, okay, that the pressure applied has to equal the pressure output. Okay, and so we come up with this idea, all right, and this is the general idea of Pascal's principle, that the force applied over an area has to be equal to the force over applied in the other area, okay, and this has to be in a closed system. So that means that these two areas, the only place for these forces to be applied is on these two places here. So you've got your area 1 and your force, okay, and your area 2 of your force. Okay, so you can actually use this to calculate how much force you're lifting on a truck here. Okay, so let's do a couple of practice problem here. Okay, pressure from fluids is caused by the weight of the fluid pushing down. Okay, so how would you calculate the weight and pressure from a column of water with a base area of 1 meter squared and a height of 2 meters squared? So we want to figure out the weight. Well, weight is equal to the force due to gravity, which is equal to the mass times acceleration due to gravity. Okay, well, we need the mass of the water. Okay, well, they don't give us the mass, they give us these two concepts here. From this, we can easily calculate the volume, right? Base area times height would give us our volume. And we have the density of water, okay? So we could do the volume times the density of my water times gravity, okay? So the volume would be just 2.00 meters cubed, okay, and then the density due to water would be 1.00 times 10 to the third, and this is in kilograms times meters cubed, okay, and then and so now we're just in mass because our meter cubes have canceled, and then times our gravity here would be 9.81 meters per second squared. Okay. So that means our weight would be equal to 19,000, okay, 600 newtons. All right, and now we need to find the pressure. Well, pressure is equal to force over our area. Well, our force we just found was 19,600 pascals. Okay, and our area is right here. It's 1.00 meters squared, so 1.00 or not pascals, excuse me, newtons, and 1.00 meters squared. All right, so 19,000 divided by 1 is still going to give us 19,600, and now our units are in Newton per meter squared, or pascals. Okay. All right, fluid pressure as a function of depth. This is a very good formula to know. Okay, we could derive it, but we're just going to save time a little bit because you don't necessarily need how to derive it at this point. All you need to know is that you can find the pressure at a depth by this. So this is the absolute pressure. This is the pressure that it actually feels at whatever depth you're at. Okay, is equal to the atmospheric pressure. So this is the pressure of the atmosphere pushing down on whatever fluid you're in. Okay, plus the density of that fluid times the free fall acceleration times the depth of the fluid that you're in. Okay, so essentially what you're saying is that if you're scuba diving, okay, here's the surface of the water, and say you're 10 meters below the surface of the water. This is you, this is your scuba tank, this is your head, okay, and these are your arms and you're swimming, okay, and there's your legs, okay, you're out there. All right, and so anyway, so the atmospheric pressure is pushing down on you like this, okay, and so that's pushing down on you, but then also the fluid pressure is also pushing down on you equally from all sides, right? And so really all we have to do to find the fluid pressure that you're experiencing is adding the atmospheric pressure, which we assume is constant, okay, that we gave earlier, plus the density times the free fall acceleration times the depth that you're in. Okay, so let's do a couple practice problems here. All right, so in a hydraulic lift, a 620 Newton force is exerted on a 0.20 meter squared piston in order to support a weight that is placed on a 2.0 meters per squared piston. How much pressure is exerted on the narrow piston? How much weight can the wide piston hold? Okay. So we need to figure out, okay, so how much pressure exerted on the narrow piston? Well, the pressure exerted on the narrow piston, pressure equals force over area, okay? And so the force is 620 newtons, and the area of the narrow piston is 0.20 meters squared. All right, so so 620 divided by 0.2, we get 3,100. Okay, 3,100 pascals. All right, so there's the pressure exerted on the narrow piston. Now we want to know how much weight can the wide piston hold. All right, well, weight is the same thing as force due to gravity, and we know that force of area, or force 1 over area 1 is equal to force 2 over area 2. Okay, so we want to find F2. Well, F2 would just be equal to, okay, F2 would just be equal to F1 A2 over A1. Okay, so F1, okay, is our 620, so 620 newtons. All right, A2 is 2.0 meters squared, okay, and then A1 is 0.20 meters squared, okay, so that means F2 is equal to 620 times 2 divided by 0.2. We get 6,200 newtons, okay, 6,200 newtons. All right, so that's how much weight the wide piston can hold. All right. All right, let's see. At what depth in water does the pressure double from normal atmospheric pressure? So they give us normal atmospheric pressure, and we want to know at what point it doubles. So our pressure, this is our general formula. Our absolute pressure is equal to pressure of the atmosphere, P naught, plus the density of the fluid times gravity times height. Okay. Now, in this specific case, we want to double the atmospheric pressure. Okay, so that means this is going to be equal to 2 times P naught. All right, so we're going to rearrange it. We want to know the depth, so that's really we're solving for the height. All right, so we're going to rearrange. So we're going to say, well, we're going to subtract over our P naught. So 2 P naught minus P naught equals rho g h. Okay, well, these two will cancel, right? So we'll end up with just P naught. Sounds like I'm saying peanut. It's close to lunch. P naught equals rho g h. Okay. So that means our h is going to be equal to P naught over rho g. Okay. And our P naught was 1.01 times 10 to the 5th pascals. Okay. And our density of water is 1.00 times 10 to the 3rd kilograms per meter cubed. Okay, and then our height, okay, is equal to, or the height is what we're solving for. We need gravity, so 9.81 meters per second squared. Okay, so we'll take 1.01 e to the fifth divided by 1,000 times 9.81. We get 10.3. So when you're at 10.3 meters, okay, when you're at 10.3 meters, you're experiencing twice atmospheric pressure. All right, that's when the pressure doubles from your normal atmospheric pressure, and that's it for fluid mechanics. Next unit we'll talk about, or in the next part there, we'll talk about fluid flow. It's kind of a short unit, so we're almost done. All right, hang in there, do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.